Okay, this is the review for the second exam for Cognition, EXP 3505. We begin with Lecture 7, which is the first lecture on attention, and this begins the fourth chapter in the textbook. So we started off with the demonstration of the importance of attention, and in this video, the professor was talking to some people, and the fellow was asking for directions, and the guys came through at the door. And they carried on the conversation, and this was actually a Harvard study. They found that people did not actually, majority of people did not notice that the person who they were talking to before the door came through was actually switched with a different person. And the point was that you can be sitting and having a conversation, point blank, you're taking in sensory information, and you can still miss something that happens right before your eyes. And that's because the sensory information needs to be processed. So even something as simple as recognizing that it's the same person who's standing and asking for directions, without attention and without that processing, you won't necessarily notice or encode the fact that it's a different person. And this is sometimes called inattentional blindness. Another form of demonstration that we require attention is change blindness, and we did a cog lab on this. And so if a picture is flashing with a brief mask in between and some change is happening, people will often not be able to spot the change until they're looking directly at the item on the screen. And as we showed from various other examples of inattentional blindness, this can happen if you present a mask in between, a gray screen, or even if you just flash something on the screen at the same time as the change, as long as you don't have the transient cue, so a motion cue. So if, for instance, if you just show a picture and then immediately show a different picture with the change, you will spot the change. But if as long as you present something else that means that the change doesn't provide a motion cue, then you're not going to be able to spot it very often, and that's because we're not able to process the entire image at once, and only with focal attention, only when you're specifically focusing on a specific location, do you often spot these kinds of changes. So there are these two things, inattentional blindness, change blindness, which are both demonstrating the importance of attention in terms of basic processing. The inability to detect properties of seeing outside of attention. So there are many of these kinds of demonstrations that show that even though we think we see everything all at once, even though when we open up our eyes it feels as if we kind of encode and process everything at once, in fact there's much that we do not see, and that's because we only have limited processing resources. We simply can't process everything at once. However, as we saw from this demonstration, it's not the case that you only see what's in this specific location where you're focusing attention. In the class, we briefly presented this image, and even with a brief presentation, people can usually extract the basic visual gist. So you can usually extract the general categories. So there's an outdoor scene, maybe with some basic things about people standing around. And you can get some details about the information about the scene, even without moving your attention around and looking at each part of it. So which is it? Well, we're able to rapidly process the gist of a whole scene, but we miss many details which require attention. So a certain level of detail requires attention, but we are also able to process a great deal of information outside of attention, but where the details lie, so the jet engine or a tree moving or something, a detail of the scene, we may miss without attentional processing, even change of somebody's identity if their face is changing. So what is attention? There's a famous quote from William James: taking possession by the mind in clear and vivid form, one out of what seems several simultaneously possible objects or trains of thought. And the things we want to extract from this is that James points out that attention is about exclusion. It's about that there's lots of different information that you can theoretically process, but you have to choose which information you're going to process and which information you're not. So one out of what seems several possible. And objects, as he mentioned, something we're going to talk about, or trains of thought. It can be sometimes about paying attention to your own internal thoughts, not only things external outside in the world. So why do we need attention? And the answer is, as we've hinted at, is that sensory information needs to be processed. So all of those visual processing that we talked about prior in earlier parts of the semester need to happen. You need to process figure ground. You need to process edges. You need to process depth information. All that stuff doesn't happen for free. You need your brain. You need different actual brain resources to do it. And we have this thing called information bottleneck, that you have too much information, you're only able to process a certain amount of it. So you have to choose which information you're going to process. And that brings us to the idea of attention as a filter. Sensory input comes in and we only process some portion of that information. We talked about sources of attentional control. Endogenous is top down, and that's things that come from within in terms of where you're going to allocate your attention. You can decide, I'm going to pay attention to this portion of the screen, or I'm going to pay attention to something based on the fact that I think it might be important. Whereas exogenous is based on bottom-up, cues-driven stimuli. So a flashing light or a loud sound will drive your attention and draw your attention away. And that's why in those change blindness experiments, if something suddenly comes on without the mask, if you have a sudden shift in the scene and you get a motion cue, that is going to draw your attention exogenously. Selective attention is the standard type of attention that we often think of as paying attention to something. We think of paying attention to a specific thing, a single property, object, or stimulus. And there's something called the cognitive party phenomenon that really exemplifies this. This is the ability to pay attention to a single conversation and ignore all others when you're in a crowded room where there's lots of conversations. So all that information that's out there, it's all making its way into your ears. Other people's conversations are making their way into your ears, and somehow you're able to selectively attend to the particular conversation you're engaged in. Divided attention, on the flip side, is paying attention to multiple things at once. And as I mentioned, there's some discussion about whether we actually can really pay attention to multiple things, or perhaps move our attention around quickly and toggle between them. So a very basic question in the history of attention research is, when does filtering take place? So the idea is that only a certain amount of information is processed, but what do we mean by that? At which stage of processing are we talking about that only things you're paying attention to get processed? So we talked about two models, early and late. Early filtering models say filtering happens before much processing takes place. And so it's based on simple properties of a stimulus. So in the cocktail party phenomenon, this could be, basically the idea would be that you process all of the information up to the point that you can filter out based on simple properties. So you may use the pitch of the person's voice you're listening to. Everybody else whose voice is not that pitch, you're going to selectively filter that out. And you're only going to process the meaning of the words, for instance, of the person who you're paying attention to. Could be things like the pitch of the voice, could be some other simple properties, location of the voice. And in the early filtering model, you do not process the information beyond that, just enough to be able to decide which ones you're going to continue to process or not based on these low-level properties. In the late filtering model, however, the idea is that you process all the information somewhat in terms of its meaning, and only after you've processed the meaning do you then selectively filter some of the information out to further process it in terms of really following the conversation, for instance, of the person you're paying attention to, and not following the conversation of other people, but perhaps you are processing the meaning of the other conversations and then filtering them out. So some early studies that tried to look at this and what the mechanism of filtering is a dichotic listening task, in which people listen to two messages that were being spoken to two different ears, and were told to attend to one ear and ignore the other. And the question here is if what is processed or learned or understood about the information that's coming to the unprocessed ear, to the ear that you're not paying attention to. And so, according to the early filtering models, you basically wouldn't be expected to process much about it at all, except some very basic features. And that's exactly what the early studies showed, is that people would be able, and for the unattended ear, they would be able to report certain properties, like whether it was male or female, maybe if it gets suddenly louder or quieter, but they weren't able to tell you anything about the actual content of the message. So the meaning of life, if that's in the unattended ear, they're going to miss that. And this brings us to the broadband filter model, which is an early filtering model of attention. And the idea is that messages come into sensory memory, and then this filter filters out the information on the basis of simple physical properties. So it could be things like, in the auditory domain, it could be things like pitch or location. So important point is sensory memory takes in a huge amount of information and then gets filtered and reduced to a smaller amount, and only that smaller amount ends up getting processed by the detector, which is what processes meaning. But later experiments show that some information does get through. So for instance, in the dichotic listening task, it was found that if somebody's own name was spoken to the unattended ear, people actually did hear it and were able to report it. The Dear and Jane experiment makes this even more pressing. In this case, the unattended ear, there's a meaningful message. Dear Aunt Jane is switching back and forth between attended and unattended ear. And the point is, people end up following the meaningful message. And of course, if you're not processing any meaning in the unattended ear, then you shouldn't be processing that information and noticing that this story makes sense on the basis of switching back and forth. So clearly we're processing the unattended input as well in terms of its meaning. So this brings us to the attenuator model, which suggests that it's not the case that the filter completely filters out, eliminates the unattended signal. Rather, it reduces it. So you can think of it as almost cranking down the volume on the unattended message. And what happens is that items with high importance, so for instance your own name, are detected. So it's almost like if somebody whispers your name, you might be hearing it because your name is something that's very important to you. Whereas if somebody whispers something that's completely unimportant to you, you might not process it. Now, of course, this doesn't really mean that the volume is turned down, but you can think of it in terms of the signal that your brain is sending further on for processing. The unattended message gets this lower reduced signal in the attenuator model, whereas the attended message has a much stronger signal. And they both go to the dictionary unit, but only those things that are of high importance are going to end up being noticed to the point that they make it their way to memory. So which one of these is right, early attenuator or late? And the answer, as in many questions, is it depends, and it's somewhat a complicated story. And one important factor in this is attentional load. And so it's the idea of simply dividing things up in terms of attended and unattended may be a little too simplistic. So we can think of attention as a resource, that you have a certain amount of processing resources, and the more attention we need for one task, the less resources we have for another. So, for instance, if you're doing a very high attentional load task, then you may process unattended information very little, maybe not in terms of its meaning. But if you have a less attention heavy task, then you may be able to process other information that you're not paying attention to. And this brings us to the flanker compatibility task. Flanker compatibility task is a study done by Levy in 2005 where they compared high and low attentional load tasks. So the central task here was to look for a certain target, an X amongst O's, and this is the low load condition. And then they would put a flanker somewhere out there that you're not supposed to ignore. The question is, does the flanker out there interfere with your ability to do the central task? And what they found was in the low load task, the flanker would interfere. It would add reaction time to this task. Whereas in the high load condition, because so much attentional resources were being paid to the central task, it seems very little was left over for the unattended information. So in this case, the flanker does very little and doesn't really reduce performance. The exception to that, as we said, was video game experts who showed significant interference in both the high and low load tasks. So they were getting interference even in a high load case, and that suggests that they perhaps have ability to process information outside the focus of attention because they have more processing resources that are left over for other tasks. Automatic processing is processing that requires very little or no attention, and when you're doing automatic processing, a lot of resources are left over for other tasks. We talked about the Stroop test. So in this case, if you have to name the colors of the circles, you can do that fairly quickly, but if you have to name the colors of the ink here, there's often going to be this Stroop interference, and that's because reading of these letters, reading of the words, is automatic. We do it for so many times over our lifetime that you can't help but read this word as green, and that can interfere with the ability to quickly identify this ink color as blue. And so this is a process that requires very little or no attention, so reading is often thought of as an automatic process. Divided attention, as we mentioned, is when we can pay attention to multiple things at once. We gave an example of multiple object tracking. People can track between 4 and 6 items, and in these examples, multiple object tracking, things move around the screen and you have to watch them. You have to keep track of multiple items, and the subjective experience is that you can essentially pay attention to multiple things on the screen at once. And as we said, there seem to be some specific limits on this kind of ability, somewhere between 4 and 6. Some people have greater ability than others. And one important thing to notice here is that in multiple object tracking, it really is locked on to things that are objects. It's less clear that you can pay attention to, say, 4 locations at once. But when it comes to objects, it seems that people are able to do this. So divided attention is possible, as multiple object tracking seems to suggest, but we're much worse at it than we think. And so the simple fact is that when you're allocating resource towards one type of cognition, that's going to leave less processing resources left for a different kind of cognition. And so if you're talking on the cell phone, that does require some processing resources. That is going to detract from your ability to do something else, which is like driving a car. And risk of collision is much higher. And as we see in controlled studies where people used driving simulators, people with cell phones made many more errors, like missing red lights. Their reaction times were slower. And these are things they might not even be aware of, but talking on a cell phone has this quality that it reduces driving ability. As we mentioned, it's not only the use of the hand device, even with hands-free, these kinds of effects are still there. It's really about processing resources and the fact that you need to use those in order to have the conversation on the cell phone. Okay, we start lecture 8, which is the second lecture on our attention. So we discussed how attention is allocated. Overt attention is based on eye movements, and covert attention is without eye movements. So even though eye movements are typically very strongly correlated with attention, usually where we're paying attention is where we're fixating, but as we saw in a little while, the covert attention is also possible. So attention is really about what you're processing, not, for instance, what you're looking at in the sense of what's in the center of fixation. Eye movements, as we said, are very important in terms of attentional allocation, and we just showed this demonstration of the fact that eye movements are happening all the time, and those are actually what give rise to the motion in this stimulus. And if you can stop your eyes from moving for a moment, you can get the motion to stop. But the point is, without deliberately doing that, our eyes are actually moving around several times a second. We discussed 2 types of general categories of eye movements. Saccades are short, jerky motions, and often endogenously driven. So that's most eye movements as you're reading, for instance, and you move your eyes across a page. That's going to be saccades, because there's nothing that's externally driving those eye movements. Whereas smooth pursuit is smoothly following a moving object, and it's only possible to have smooth pursuit when there's an external object. And we did that little demonstration in class. When somebody's moving their finger across, you can do a smooth pursuit of that. But if you try to do that and emulate that, you can only endogenously produce saccades. So saccades are these meaningful movements that are very highly correlated with the task at hand. And so this is a typical saccadic fixation. We often fixate locations a little bit before we're about to act upon them, and it makes perfect sense. You're figuring out where the items are that you need to interact with, and then you initiate the motor action. And so this happens very quickly. By a fraction of a second before you interact with something, you typically move your eyes there. What drives eye movement? So of course motion, as we said in smooth pursuit, but if you're looking at a still image such as this one on the left, and you are moving your eyes around endogenously, what's driving that is, first of all, bottom-up cues. Things that are driven by the stimulus itself, and there's something called a saliency map, which can actually produce this automatically, and it's based on things like locations where there's large changes in color or luminance, and it's similar to the edge detecting type of algorithms we've talked about before. So they have this big blotch of color that's going to show up here, and you have this big white spot over here that's going to show up. And these things can be shown to do some of the work in terms of explaining where our eyes go when we're surveying a scene. But there's also top-down cues. So if somebody is told to look around a kitchen and look for a pot, they're going to look in reasonable locations for that pot. They're going to search in unlikely areas. And so that's based on top-down information. One knows where the items are likely to be within a certain environment. As we mentioned, in this study, they also found that people's expectations about where items are likely to be can drive their amount of time that they spend looking at a specific location. So if an item is floating in the air, for instance, or if it's an item that doesn't belong in a specific location, people may spend longer fixating it. And again, so it's top-down expectations that are driving fixation behavior. Those are all examples of overt attention. It's based on eye movements. Covert attention is also possible, and in this example that kind of failed in class, but if you're looking in a location here, you can process information that's happening outside of where you're looking. So attention can change the input in the sense of changing what you're looking at, so depending on where you're looking, your input's changing. And the reason we foveate, as we mentioned, is that you want to bring things into central fixation when you want to pay attention to something, because that's where the highest resolution is. But sometimes you may want to look here and then focus your attention elsewhere. And so even without changing the stimulus, because your eye is staying in the same location, you can change the processing of the stimulus. And that's covert attention, where you're changing processing without doing the overt change in fixation. Then we discussed what types of things we can pay attention to, and we've talked about three basic ones: locations, properties, and objects. We discussed Posner's famous 1978 experiment showing that people can pay attention to locations, and they can do so in a covert kind of attention task. And you guys did a cog lab on this. People would be given, would look at a central fixation and maintain fixation throughout. They wouldn't move their eyes and were given a cue, and the cue was either valid or invalid. And then what the valid meant is that on valid trials, there would be some target that would show up in the location that the cue was pointing to. And what was the general finding was that if it was a trial where there was a valid cue, reaction time was quicker in responding to the stimulus. And the idea is that people are processing that information in the location even prior to the target showing up, and they're doing this in a covert attention kind of way. So this is evidence that people can pay attention to locations and that this can speed up their responses, their ability to process information there. Also some evidence that we can attend to specific properties. So this is a study of Franklin and Eve, where they found that if people had to repeat letters of one color and ignore the numbers, so let's say in this case you had to repeat the letters, the red letters X and G, the fact that there are black numbers as well doesn't interfere with that ability, but the red numbers will interfere, and that suggests that people can kind of filter out the black and just process the red. And when we talked about, again, early filtering models, in the visual domain, an early filter might filter information on the basis of color. And this would be evidence that people are able to do that in this case, so they don't even process the meaning of the black items, and therefore they don't interfere with the red items that you need to identify. So this is evidence that people can pay attention to properties, not just locations, in this case color. And there's some evidence that people can pay attention to objects as well. And this is Egley et al. And there are various other studies along these lines. And what people had to do here was they were maintain fixation similar to the Posner experiment, and then they would be given a cue, and then a target would show up somewhere. And the finding here was that if the target showed up somewhere that's on the same object as where the cue was, people are faster. So if the target appeared in location 1, people were faster at identifying it because it was on the same object as where the cue was shown. And if it was shown on 2, even though it's the same distance away from the cue, people are slower at identifying the target in this case than in this case. The idea being that attention actually spreads to objects. And so when you're paying attention to somebody, you're not just paying attention to their eyes or wherever in their face you're looking. You're paying attention to their whole face, and potentially, if they're standing a couple of feet back, you're paying attention to the entire person. Attention spreads throughout the entire object. What does attention do? And so we talked about some evidence that attention can actually enhance contrast sensitivity. things actually look like they have higher contrast when you're paying attention to them when you're not. And so Carrasco showed this in a controlled experimental environment, showed that the appearance of items that are being paid attention to actually has higher contrast. And higher contrast in this example is just the fact that as things are going lower and lower, they're getting reduced contrast. And so something that we think attention can do is maybe turn it from something that looks like this into something that looks like that. It has higher contrast. And so therefore, that's because you're processing it more. And so that increases the degree to which you're actually processing its features, and it's to some extent equivalent to it being more clear and having higher contrast. What else does attention do? What's attention good for besides perhaps enhancing contrast? And feature integration theory is a very influential theory proposed by Anne Treisman back in the 80s, actually. It suggested that what attention may be doing is taking multiple features of objects and combining them. So as we mentioned, different parts of the brain process different properties of objects: color, orientation, motion. These are handled by different portions of the brain, and the question is, how are these bound together to in order joined together to have a coherent object? And so feature integration theory says that attention is needed to combine information from different parts of the brain. And so we discussed several sources of evidence for this, from visual search and illusory conjunctions. So in the visual search case, we compared different kinds of search stimuli, and these are some examples. So these are single feature searches. In these cases, for instance, you have to find the green item amongst the red items, or the tilted blue item amongst the other blue items. And the basic finding is that if you have a few distractors, you have many distractors. As you add more and more distractors, it doesn't add to the search time. And this is sometimes called pop-out search. The idea being that you don't really need attention in order to detect that there's something that differs on the basis of one property. However, conjunction search is a whole different ballgame. If you have to detect, in this case, the upright green item, that might require quite a bit more time because it's a conjunction of two properties. You can't just use green and you can't just use upright. You have to find the one that is both green and upright. And in order to do so, you need to find a conjunction of features. And the finding in these cases is that the more items you add, and the more elements you add to this stimulus, the longer it takes people. And it does it in a linear way. So if you add one more item, it adds that much more time. You add 3 more items, it adds 3 times more than adding one item is. And that's the linear relationship. And the explanation for that is that, that's been proposed, is that in order to solve this task, you actually have to serially, this is called serial search rather than pop-out search, and you have to serially move your attention from each item and test whether it has this conjunction of features. And so as you add more items, each one more item means that's one more thing you have to check. We also discussed the positive and negative. Positive, if the item's there, is going to take longer than if the item's not there, not responding that it's not there. And that's because in the positive case, you're usually going to have to go through about half the items before you actually come across it. And this is why it's hard to find your car in a crowded parking lot, because you usually need to do a conjunction search. Cars have similar shapes. Maybe your car has one different shape, but other cars have that same shape. And then you have to find the conjunction of shape and color in this case in order to identify your car. And that requires serially searching through all of the different cars. So it's highly inefficient. Another source of evidence for the fact that attention is needed to integrate features, to combine features, is illusory conjunction. So that was an example there, and that we saw in class. And the idea in this case is people have to report the numbers on the two black numbers on the side, and then have to report the letters. And what often happens is that in many about a third of trials, people will correctly remember the certain colors and correctly remember certain letters, but they'll falsely report the conjunction. So they'll remember, for instance, a red X in this case, or a blue T. So the idea is that they're separately processing those individual color features, but in order to conjoin them, in order to know that there's a blue X, which depends on two features, shape and color, that requires attention. And if you're busy looking at these two numbers and this quickly flashes, you don't have time. And so what you do is you then try to combine them after the fact without being able to allocate attention, and you can get it wrong. Physiology of attention. As we mentioned, there's multiple brain areas, but several that have been identified are the parietal and temporal. Parietal is considered very important, and also frontal. So there's three different brain regions that have strong relationships to attention. And this task we will mention was where people were given a cue as to look for a certain direction of motion, and on some trials they had to detect that particular motion direction when it showed up, and in some cases they just had to passively view it, and that's what they did as a basis of doing the comparison. Same stimulus, but in some cases you have to pay attention to look for the motion direction, in some cases you're not. And what they did was record from the time period before the motion stimulus actually showed up. And this way you know you're just gauging what attention is doing, not the motion stimulus itself. Single cell recordings have also been done that show that certain individual neurons will show a difference if, in this case, a monkey is fixating and a stimulus turns on. This cell does not respond very heavily, but if they're fixating here and they have a task that they have to do with this location over here, then you'll see a stronger, more vigorous response, and that suggests that this neuron is actually being modulated by the attention, by, in this case, covert attention, because they're fixating in this location. But this is a neuron that's responding, and it's responding differently on the basis of whether they're paying attention to this location outside of fixation. One thing we mentioned is that these differences, these modulations due to attention, become more pronounced higher up in the visual stream. And again, this comes down to the idea of filtering. So early on, you're doing very little filtering. It's not going to really matter if you're paying attention or not. At the level of the photoreceptors, attention is meaningless. As you get a little further up, maybe attention is modulating somewhat. And as you get even higher up, so let's say face area, you would expect attention to be very important because you're not processing the meaning of stimuli outside of attention. So those neurons that are responsive to those higher level features may only respond if you're paying attention. Then we also discussed some deficits of attention. Attention deficit disorders, which is a very prominent and commonly diagnosed disorder, is characterized by an inability to focus on a specific task, and may involve pure executive functioning, the inability to suppress or filter irrelevant information. So if we think about a flanker compatibility task, a attention deficit patient might have an inability to not pay attention to that irrelevant flanker. And so if there's something interesting happening, it's not just that they're weak-willed and can't stop themselves. It's that they almost automatically are perhaps processing information that's outside of what the central task that they're trying to do, and that's naturally going to draw away resources from the central task. We also mentioned memory degradation due to aging is now thought by some researchers to be partially due to inability to suppress irrelevant information. So why do elderly people start to lose their ability to remember something that something that just took place? May partially be due to their inability to, during encoding, to only focus on that. Perhaps they're also automatically processing other information that isn't relevant. Balin syndrome is a fairly rare syndrome where people are unable to fixate on individual items, and so they can't look at the red X or the blue T or whatever the case may be, and so therefore they may actually experience illusory conjunctions. So they kind of spread their attention all around at once without being able to do real selective attention. Simultaneagnosia is kind of the opposite of this, and this is the inability to focus on multiple things at once. So simultaneagnosic might only be able to report one property of a scene and not be able to move attention to something else. And so therefore they will almost be essentially blind to these other items in these kinds of scenes because their attention is so stuck on one portion. And a related kind of syndrome is visual neglect, where attention is allocated to only one visual field, and very often it's the right visual field because it's often due to damage to the right hemisphere, which leads to neglect of the left visual field. And what patients with visual neglect will often do is if they have to copy something like this cat or this clock, they'll only copy half of it. And they'll essentially ignore the other half. If it's pointed out to them, as we saw in the video that we watched in class, they can see it. It's not as if they are blind, literally blind to it, but they do have this kind of neglect that happens. So it's sort of an inattentional blindness that happens to one visual field. And finally, we discussed autism and attention. So one of the characteristics of autism is that there's inappropriate or unusual attentional fixation. So in a movie scene, for instance, neurotypical people will look at the eyes in this case, because this indicates that there's something interesting happening and we're viewing this person's eyes, whereas autistics will often look in locations that seem to be more having to do with local contrast rather than important cues having to do with social information, such as where people are looking. We move on now to Lecture 9, which is the next chapter, Chapter 5, Short-Term Memory. So what tasks do we need memory for? And as we pointed out, in fact, there are many tasks that we need memory for. We think of memory often in terms of long duration. So when we think of memory, we're often thinking in terms of long-term memory, things that people remember information throughout their whole lives, their childhood, they remember their wedding throughout their entire lives. But there's also short duration, and we saw beta movement, which it's not going to work right here, but when a little dot is moving across the screen, this requires memory, because knowing that the dot is moving from the left to right requires that you, at each new location, you have to have encoded that this thing had a location a moment ago that was to the left, and now it's moving from left to right. So even something as simple as motion perception requires some form of memory. One of the shortest forms of memory that we can record is something called the persistence of vision. And this is a memory that takes place within our sensory system itself. So if you take a coin and you shake it back and forth, if you do it quickly enough, you can see the coin in multiple locations, and that is because the residual image actually stays within our photoreceptors or in our retina for a certain amount of time after it's already left. And so that's how you can see multiple coins at once, is because as it's moving around, it hasn't quite disappeared from the location it was in before. And as we mentioned, standard good old-fashioned photo projectors were based on persistence of vision. The way they worked is that the reel would go and stream past, and then there would be a light flickering on and off. And as long as the image was shown in succession for a short enough amount of time, so somewhere around the range of like 25th of a second, even though there was an interval of black in between each picture, people would not detect that, and that's because the persistence of vision was such that the picture would stay on their retina until it was replaced by another picture. So what test do we need for memory for? A better question is, what cognitive ability doesn't depend on memory? Most cognitive tasks, or just really anyone you can think of, depends on memory. So we started with a basic definition of what memory is, and these are three very important components of memory. So memory depends on encoding, storage, and retrieval. And encoding is the input, storage is what it sounds like, storage of the information, and retrieval is output whenever you have a behavior. So it could be behavior such as actually reciting a list that you learned. But any behavior that depends on information from the past is going to depend on these kinds of memory, is in essence something that requires memory. So when we're talking about memory and different kinds of memory systems, we can talk about various properties, things like capacity and duration. So capacity has to do with what kind of information and how much information something can hold. So you can have different buckets holding different kinds of stuff, and then different amounts of stuff that they can hold. And this turns out to be a useful idea when it comes to memory systems. And besides what kind and how much, we can also back to duration, which is how long can information. So here's a leaky bucket. How long does it have that it can hold the water until that information is lost from memory? We begin with the modal model of memory, which is a very influential model that suggests there are in fact three different types of memory systems: sensory memory, short-term memory, and long-term memory. And sensory memory is some visual persistence is an example of sensory memory, but we're going to see some other types of sensory memory as well. It's this very high capacity but short duration type of memory, holds a lot of information. And then selective attention operates over sensory memory, and then only a certain portion of the information makes it into short-term memory, Short-term memory is where certain kinds of information is held for a certain amount of time until you're able to do something with it. And then that information in short-term memory, some of it makes its way to long-term memory. In addition, long-term memory, you can take information from long-term memory and bring it into your short-term memory to hold it there as well. So short-term memory is a holding place, and it's also until you're able to do some sort of output with it, and also a path to long-term memory. So we've discussed sensory memory, and so characteristics of sensory memory, it's very high capacity, holds a lot of information, but for a very short duration. And we focused on visual and iconic memory, as it's called. So an icon is an image, and there's some studies that have suggest that people actually maintain almost a photographic-like quality or richness in memory, but just for a brief amount of time, somewhere in the range of 1 second. And we discussed some evidence for this from a famous study by Sperling, in which people, and which you did for a Cog Lab, which people are presented with a grid, and if they have to, if the grid is presented and then briefly shown and then disappears, and then people have to report as many letters as they can usually remember somewhere in the range of 3 to 4 total items from the grid. In the partial report, and that's the whole report condition. Partial report condition, which is the Cog Lab you did, you have to report items from a specific line in the stimulus. And what's important here is that the stimulus appears, disappears, and then you receive the cue as to which line you need to report. And the finding here is that people can remember between 3 and 4 items from each line. And what this suggests is that the entire stimulus is available in memory, and then when given the cue, because remember, the stimulus is gone. So then the stimulus is gone, and then you're told which thing to report. The idea is that people are able to read off any individual line that they're told to read off, which suggests that the whole stimulus is held in memory for a brief amount of time. Well, how long? And there is an example of it. How long does that happen? Well, if you look at the decay function here, as the tone is delayed from presentation until you have to do the report, until you're given a tone and told which items to report, which line to report, it very rapidly declines, and from 0 seconds, and by the time you're out to 1 second, performance is similar to the whole report, which means you no longer have the whole grid available to you. And so it's thought that this form of memory, iconic memory, lasts anywhere up to about a second. But as you see, even within that second, there is a gradual decline, or I should say a rapid decline. Between 0 and 1 second, information is declining as you have to wait for that tone. And so the idea is that the whole grid is held in memory, but it's quickly declining up to the point where about a second out, it's no longer there. And so the partial report in the whole report condition, and what happens after a second, is that whatever line of code or whatever strings you read off are now held in short-term memory, and that can last beyond a second. So what's short-term memory? According to the Atkinson and Schiffer model, short-term memory is a place to hold information so that you can do something with it. And then it can also rehearse that information so you can hold it in there longer. So according to Atkinson and Schiffer, that's the basic purpose, is a place to hold information you need for current task, and it's also a path to long-term memory. And as we said, what I mean by one-way path here is that this is the only way you can get to long-term memory. You need to first go to short-term memory in order to get to long-term memory. So what's the capacity and what's the duration of short-term memory? How many items can it hold, and how long does that information stay? So in terms of how much information, we discussed Miller's magical number 7. 7 plus or minus 2 items. So if somebody's read off a list of letters or names, the typical capacity is that usually they'll remember 7, or sometimes as low as 5, and sometimes as high as 9, depending on the individual. So what counts as an item? What it counts as when we say there's 7 items, and as we mentioned, there's this phenomenon of chunking. So if I give you numbers that each one of which a series of numbers, and a series of numbers that can be combined into one number, so something like 2013, that might be remembered as a single item, not as 4 items. And clearly it's related to long-term memory. If something in short-term memory matches something in long-term memory, that can be chunked into a single item, and people can remember In that case, many more than 7 of the individual smaller items if they can each be chunked into a larger one. And so what we can remember are 7 chunks. And some evidence for this came from chess experts who have been shown to be able to remember many more chess configurations than a beginner if they've shown a chessboard, but that only applies for legal actual game positions. But if it's random placement, then they can't. And this suggestion is that the reason they're able to remember actual game positions is because they can chunk some configuration into a single item, and then they can remember more of those. Whereas a beginner is able to chunk and therefore has to remember the individual pieces. Get to a random placement, and then even the chess player is not able to chunk anymore because these are not meaningful configurations, not tied to long-term memory, and therefore will be just as poor as the beginner in remembering the locations of those chess pieces. Okay, we talked about capacity, but what about duration? How long can information stay in short-term memory? So theoretically forever, as long as you can rehearse it. So if you hear a phone number and you have nothing else to think about, you can repeat it to yourself many times, and then you can hold it there for quite a long, as long as you don't have anything new information that comes into long-term memory. But what about without rehearsal? And so Peterson and there was a task you did, Brown and Peterson, for a cog lab, came up with this idea of having people do some peripheral task, in this case counting backwards by threes, after they had been presented with some information. So people would see a trigram, they would see 3 letters, and then had to count by threes and later say what those 3 letters were. And what they found was this decay function. And it starts off with very high fidelity after 0 seconds, if they immediately have to repeat it. Pretty good all the way out to say 3, 6, 9, but then you really get a degradation performance. And by the time you're at 18 seconds, performance is very poor, and that to them suggested that the duration of short-term memory is somewhere in the range of 15 to 18 seconds, according to these studies. So what is this decay? Why do things decay in memory? And you could ask this about any memory system. It could be sensory memory, short-term memory, or long-term memory. And there's 2 possible reasons why things could decay. It could be just due to passage of time. As we said, this ultimately memory depends on states of the nervous system, and the nervous system is very dynamic, and it's changing over time. And maybe information just gets lost for that reason. Second hypothesis is interference from new information. So if you have information in short-term memory, new information comes in, it can knock out older information. We discussed 2 types of interference. Retroactive interference is information now is reaching back and interfering with information from before. So that's retro, when something is retro, it refers to reaching back to the past. And so studying for, say, this exam, let's say, may interfere with some studying that you did earlier in the day for a different exam, causing interference. Hopefully not, but that would be retroactive interference. Proactive interference is the opposite, where information now is interfering with information that you're going to learn later. So if studying for this exam causes interference for an exam you're studying for afterwards, that would be proactive interference. And Peterson we mentioned that study attributed their forgetting to curve to decay, but additional studies have shown that, in fact, it's not as simple as that. That if you reanalyze the original data, Kepler and Underwood did this, they found that the big difference between 3 and 18 seconds that shows up in Peterson and Peterson studies only happens in later trials. Later than the first trial. So in the first trial, you do not see that kind of difference if you just analyze the first trial. So if it's pure decay without any interference, then you would expect it to decay regardless of whether it's the first trial, second trial, third trial. What they found is that you do need interference as well. So by the second or third trial, you start to see this kind of degradation. And it's still degradation due partially to decay because it's happening over time. The idea is you're also getting interference from the fact that you learned information, you heard a bunch of these trigrams before and that you had to remember. And so when it's information from the past interfering with information from now, which in this is proactive interference, is information that they were learned at the beginning of the experiment, is interfering with information that they had to remember later on. So the bottom line is, what causes the reduction or loss of information in short-term memory? And the answer is it decay or interference? And the answer is, it seems to be both. You don't really get this kind of just straight up time decay unless there's also some interference. But once there's interference, you do see a time-based component, and the further out you get, the more degradation you have to memory, and to the point where, again, as we said, 15 and 18 seconds, your short-term memory seems to no longer be reliable. Okay, now we move on to lecture 10, which is the second lecture on short-term memory. And then we asked, what is the representation of information in short-term memory? How is that information being encoded? It can feel as if we store information in memory in its original sensory or modal form. So when we hear a sentence, such as the sentence I'm speaking right now, and then you have to remember it, so think about that sentence. Okay, you did it, right? Now, in a certain sense, you probably had to you kind of felt like you were replaying my voice in your head. And this is introspection, so we have to ask, is this true? Is there any basis to think that the information is actually encoded in terms of its original sensory form? So we talked about rotation, mental rotation, something that we studied earlier on in the semester, and Shepard and Meltzer's study was to some extent geared towards answering this question. So if you have to do some task, a mental rotation task, and you're engaging your memory in order to do it, does the visual memory have characteristics that are similar to actual visual stimuli and visual manipulations? And the answer was yes in this case. And so the more offset the item was, just as if you had to physically rotate it, the mental rotation looked very similar, and so it suggests that there's something kind of visual about visual memory. And in the case of auditory memory, so things like word lists or these individual letters that people have to recall, there's also evidence that it's really stored in terms of an auditory code. And so Conrad's study showed that people would often mistake letters that sound similar to one another in short-term memory, and it suggests it's really encoded in terms of the sound that it makes. So is a short-term memory a single memory system, or is it multiple memory systems? So we have the visual short-term. It seems like there's visual memory. It seems like there's auditory memory. The question is, are these in fact distinct from one another? And so Brooks did a study where he compared performance in verbal and visual memory tasks using verbal and visual memory using verbal and visual tasks. So let's see what these look like. So a person might have to do a verbal memory task, listen to a sentence, and then decide if each word was announced. So you're thinking about the sentence. We have to do a visual task, visual memory task, in which case you have to, here's a letter, and you have to do something with that letter in memory. And then they had to either do a verbal kind of response, where you say yes or no to the question, or point to an answer on a grid. And you could do these either you could have a verbal memory task and then have to do this verbal procedure, or you could do a memory task and do the visual procedure, or vice versa. And what they found was there's specifically interference when the task, the way you had to do the response, so if you had to do a verbal response, would particularly interfere when the kind of memory you had to do was verbal memory. And the same was true for the visual. So when you had to do a pointing task, that would be particularly hard if you were trying to do a visual memory task. So this suggests that there are in fact perhaps different stores for visual and auditory memory, and because those retain the characteristics of the most sensory modality. So when you're doing a visual memory task, you're really engaging your visual system to some extent, and so if you then have to do a different visual task like this one, that can interfere. But if you have to do an auditory task, it doesn't. This brings us to the working memory model of short-term memory, which came after the Atkinson and Schiffer model, and suggests a more active model of short-term memory, not just storage. So short-term memory in this case consists of three separate components: visual sketchpad, phonological loop, and the central executive. So the working memory model also makes the distinction between visual and auditory memory very explicit, and also has this additional component, the central executive. And what that's doing is You can have the phonological loop and the visual spatial sketchpad, and these are for different things. Phonological loop is to hold that information in memory and replay it so that you can use it. Visual spatial sketchpad is to hold visual information in memory but also to be able to manipulate it. So if you're doing a mental rotation task, for instance, you're engaging your visual spatial sketchpad. And essential executive coordinates between these two, toggles back and forth as to which one you're actually paying attention to at any given moment. We mentioned that there are very large individual differences in working memory. So working memory span has been shown to be very variable and consistent. So as I mentioned, 7 plus or minus 2. So there's a high degree of consistency, and some people seem to just have a shorter memory span than others. And what additional studies have shown is that the working memory span has been shown to be fairly strongly correlated with general intelligence. Surprisingly strongly correlated. And this specifically applies to fluid intelligence, abilities to process incoming information. And as we mentioned, degradation of short-term memory can actually be a sign of onset of dementia. And so there's a strong correlation here between short-term memory, which seems like it's its own little thing, and other abilities. And it suggests that short-term memory may be very important in certain kinds of cognitive abilities. So what's driving these differences in short-term memory abilities? And there's some very interesting suggestions that what really may be behind them are the inability or the ability of the central executive to suppress irrelevant information from short-term memory. As we mentioned, there's decay in short-term memory, but very heavily influenced by interference. And so people's short-term memory capacity may be strongly influenced by their inability or ability to keep out irrelevant information. And so this was a recent study, Vogel et al., 2005, where people had to do different kinds of memory tasks. They had to either remember 4 items from a memory array, or they had to remember 2 items from a memory array. And what they did was measure the EEG response of regions of the brain that are associated with short-term memory, and looked at how hard those portions of the brain were working when they had to do different kinds of memory tasks. So either a 2-item task or a 4-item task, 4 items or 2 items with 2 distractors. And what they did was compare people who were previously in short-term memory tests showed to have a high capacity or lower capacity. What they found is the high capacity individuals, when there were 4 items on the screen, their brain was working short-term memory was working hard. When there were 2 items on the screen, but also 2 items, but then they had, and then 2 distractors, their brain didn't work as hard because they were able to filter out those 2 distractors and not recall them in short-term memory. Whereas lower capacity individuals, if there are 4 items on the screen, even if they didn't have to remember all of them, their short-term memory was working just as hard. And that suggested that they're, in a sense, processing irrelevant information in short-term memory. And as we said, this in relation to attention deficit, it's a similar kind of potential problem. And even in early onset of Alzheimer's, this inability to selectively filter out irrelevant information and keep it out of short-term memory. But as we said, short-term memory is important, but it's not everything. And we watched a video of this chimpanzee. So chimps have much better short-term memory capacities than we humans do. They seem to be able to remember 10, 12 items compared to our 7 plus or minus 2. And they're certainly not more intelligent than we are. So short-term memory has its places and uses, but it's not the be-all and end-all of cognition. In terms of where working memory takes place in the brain, so like other forms of memory, short-term memory is distributed in many different parts of the brain. There isn't a single part of the brain that does working or short-term memory. Instead, it's highly distributed, and its distribution is based on which part of the brain encodes that kind of information in the first place. So objects, for instance, are going to be, you're going to see distribution of working memory taking place in the inferior temporal cortex, and that's where we know that objects are first processed in terms of visual processing. Verbal and numbers often are in the frontal and parietal, and where executive function is, and so logical reasoning And language, for instance, is in the Broca's and Wernicke's areas, and you see working memory showing up in those places as well. So it really seems to be not that memory doesn't seem to be a separate system, but rather it's the encoding, storage, or retrieval of information that's encoded in those places in the first place. So frontoparietal, also the cerebellum, which is a non-cortical structure, also is involved in working memory. As far as single cell recording, there's also some nice studies that show individual neurons whose response is modulated by memory. So in this task, a monkey would be looking at fixation here, and then a square would come on, and they would record from a specific neuron. And it would fire somewhat to the square, but then when the square disappears, if the monkey has the task of remembering where that square is, because it then later has to move its eyes there, you see that this neuron goes kind of crazy when the square goes away. And that suggests that these neurons are really coming into play, coming online, specifically when the memory of that information is required. So neural response to stimulus will fire here while the information is being held in short-term memory. Okay, we move on to the next topic, long-term memory, and this corresponds to Chapter 6 in the textbook. So long-term memory is anything from 30 seconds up to 90 years. As we said, short-term memory lasts up to 15 seconds, maximum is potentially 30 seconds. Anything beyond that would technically be considered long-term memory. So short-term memory and long-term memory interact, and this is a picture from the textbook. What you're seeing here is somebody's having a conversation, and they're engaging in short-term memory in terms of processing the specific information that somebody's currently saying to him, but engaging long-term memory in terms of thinking about the meaning and further elaborating on that information in short-term memory. So they are connected. There's bidirectional flow between short-term memory and long-term memory. Something you can maybe pull stuff from long-term memory, think about it in short-term memory, and something in short-term memory may cause you to retrieve something from long-term memory. What's the difference between short-term memory and long-term memory? Well, short-term memory is encoded in terms of the physical characteristics of the input. So it's much more specific to the particular way in which the information was conveyed to you. You can remember specific words. You can repeat an entire sentence. You may remember the intonation. You may remember visual characteristics of information you saw, whereas long-term memory is abstracted away from this to the meaning of the input. And we saw an example of that from listening from the case of a story. So everybody knows the story of Little Red Riding Hood and maybe remembers a lot of the same details. But in terms of remembering the specific words that were used to convey this story to you whenever you first heard it, typically the information, you're not going to have that information. What you do is you retain something that's abstracted away from that retains the basic meaning of that information without recalling the specific physical structure of the sensory information that first conveyed that to you. So what information is there? That there are two types of memory, and we talked about neuropsychological data. There are patients who have very severe anterograde amnesia, Clive Waring patient and HM, Jimmy G, who's discussed in your textbook. And in the case of severe anterograde amnesia, these patients will often show complete inability to form new long-term memories. However, we watched a video of Clive Waring, so it was a very profound form of anterograde amnesia. Also has some retrograde amnesia, but complete and total anterograde amnesia, inability to form long-term memories. 1 minute after he has an experience, he completely forgets he had it. But if you look at these patients, they often have perfectly functional working memory or short-term memory. So they can remember a list of words for up to 30 seconds. And that, of course, is a form of information. They're learning new information, and yet they're able to learn that information and recall it. And so short-term memory is functional, but long-term memory is extremely impaired. And this suggests that these may depend, again, on separate kinds of brain systems and separate cognitive structures. What about the other way around? Can you have intact long-term memory and then depleted short-term memory? And the answer is there are some examples of that. Patient KF had very severe short-term memory deficits, but was able to remember long-term memory episodes from way back in her life. And as we mentioned, Alzheimer's disease also has a characteristic that you can see some depletion of short-term memory capacity even before any deficits in long-term memory are apparent. Much of the research on long-term memory, as we mentioned, has the characteristics that it uses word lists as the procedure by which memory is tested. And as we'll see later in this review and later in the semester, it's not the only kind of memory that exists. There's also things like episodic memory, implicit memory. But much of the research on long-term memory has used this kind of explicit recall of specific word lists. So we know that there's encoding, storage, and retrieval, and the question is, what determines what makes it into long-term memory? So a very important component of what makes it into long-term memory is attention. And we can see this in Broadbent's filter model. As we know, in the simple early filtering model of Broadbent, only information that makes it through the filter gets processed in terms of its meaning. And as we said, meaning, and so the detector in this model is processing meaning, and we said meaning is the means by which information is encoded in long-term memory. And that's what gets sent to memory, is the meaning. And so if you don't have attention, then that information's meaning doesn't get processed or as processed, and therefore it's much less likely to make it into long-term memory. And we discussed a study briefly that showed exactly that. People who are engaged in a different selective attention task, any items that are unattended end up not making it into long-term memory. What else determines what's encoded? So attention is one thing. What else might be a factor in terms of encoding long-term memory? So we discussed the serial position effect, which is when people have to learn a long list of words, there's often a U-shaped function in terms of when they heard the word and how well they remember it. So there's a primacy effect. Words early on in the list are remembered fairly well. Words towards the end of the list are remembered the best, and words in the middle of the list are remembered more poorly. So the recency effect is usually attributed to primacy at the words at the beginning of the list and recency at words at the end of the list are better remembered. So why? Well, recency is usually thought of as being because information is still in short-term memory. That's why you remember that. Primacy, on the other hand, is thought to be because you have time to rehearse those words because they're early on in the list, and throughout the rest of the experiment you have some time to keep them in your mind, and those end up making it into long-term memory. And so this suggests, and as we said, we look at the Atkinson and Schiffer model, has this rehearsal, which is a control process, and that also may lead to the information being stored in long-term memory. So just repeating information can facilitate that information making it into long-term memory. However, as we said, pure exposure is not sufficient. You can see a penny many, many times in your life, but if you don't pay attention to the details, just pure exposure, just repetition, doesn't actually lead to very rich and well-remembered encoding. So people will often forget key details, which way Lincoln is facing, where the date goes, despite lots of repetitions. So what else might account for what makes it into long-term memory? And an important theory is Craig and Lockhart's level of processing theory, that the more deeply you encode something, the better you remember it. And so Craig and Tulving did some studies, seminal studies that showed that there are differences in how well you remember information based on how you encode it initially. So subjects had to answer different kinds of questions about lists of words, and we did this as an in-class experiment, and they had to either respond to whether the letters were uppercase or lowercase, whether the word rhymes with a different word, or whether the word fits in a sentence. And the point is that this is a very superficial, the case is a very superficial form of encoding. Rhyme requires that you at least figure out what the word is, but not necessarily its meaning, and then the sentence requires meaning. And the overall findings are that the worst performance is in the most superficial form, which is the case. Performance is better in the rhyming case, the rhyming condition, when you have to encode it in terms of the sound of the word. And the best performance by far is when you have to encode it in terms of the meaning of the word. So deeper processing leads to better memory for these words. Another thing to note here is that the yes cases tend to outperform the no cases. So when the word does rhyme versus when it doesn't, when the word does fit in the sentence versus when it doesn't. And the idea is that to the extent that you're processing that information, you're processing it more fully when it's a positive response versus a negative response. So when the word fits, this leads to a richer encoding, and when it fits into the sentence, it leads to a richer encoding when it's embedded in a sentence that within which it makes sense. However, there's additional research that suggests that it's not all about encoding. So you can initially encode something, and as we know, memories consist of three processes: encoding, storage, and retrieval. And if you're not able to retrieve that information, then your memory isn't worth very much. So there's the idea of a cue, that sometimes we need a cue in order to retrieve information. Somehow we need some way, some index that will dig up that memory and pull it out of storage. And what Morris found was this idea of transfer appropriate processing, that the ability, the quality of memory isn't only dependent on whether you encoded something deeply or not. It can depend on whether the retrieval cue matches the way in which you learned it. So what Morris did was have people, it's very similar to the Craik and Tulving, had people learn word lists either where they had to process the meaning of the word, or they had to do some sort of rhyming test. Does it rhyme with goat? Or does the blank dove off the diving board? And then you had to decide whether that fits. And so according to levels of processing, we would expect that the meaning would lead to the best memory. However, what Morris did was during the test, he asked people to remember the words in different ways. Subjects had to either perform a standard recall task or they had to do a rhyming recall task. What rhymed with simmer? And what they found was, what Morris found was that if the initial word had been encoded in terms of its sound, so in the rhyming task, then now if they had to remember it based on a rhyme, based on whether it rhymed with, say, simmer, they were better at it when they had encoded in terms of the rhyming versus when they had encoded it in terms of the meaning. So it's not as simple as simply saying that no matter what, if you learn the words in terms of their meaning, that's definitely going to lead to better memory. It also depends on the nature of the retrieval cue. So the way in which something may jog a memory, something may cause you to remember something, depending on what that causes, depending on the nature of the retrieval cue, that can change your ability to remember something or not. However, one important point here is that in a standard recall task, semantic wins. Generally speaking, if all things being equal, it's better to encode information in terms of the semantic meaning if there's no specific retrieval cue that has to do with something else that doesn't have to do with the meaning. So implications for studying, for instance, you probably shouldn't try rhyming the words that you're learning, the terms that you're trying to learn. Much better off learning the meaning of those words and encoding it more deeply. Another example of retrieval cues being important is Tulving and Pearlstone. They found that if people learned words that came from certain categories, so let's say people learned a list of words made up of the categories birds, furniture, a bunch of different categories, but people weren't told when they were learning them that they were made up of these categories. Then later on, they had people either just recall the words, tell me all the words you remember from the list, or they told people there were 3 categories of words, now can you list them? And people did much better when they were given the categories, and that's because those categories serve as retrieval cues. Oh, it was a bird. Now I remember I saw an ostrich or a penguin. And so given that retrieval cue, that helps people to remember. And this is, again, a very familiar idea that when somebody gives you some sort of hook or a cue, that can help you to retrieve memory. As we've said, this is kind of intuitive, but there are less intuitive examples of retrieval cues where it's not an obvious logical connection between the retrieval cue and the items that you have to remember. So, for instance, there's just idea that where one learns the information, the situation in which one learns the information can serve as a retrieval cue. In this particular example, the 1975 diving experiment, participants learned words either underwater or on land. And then they were tested either underwater and on land. And the basic results were that people who studied the list underwater remembered it better when they were later tested underwater than when they were tested on land. And the opposite was true as well. For those who learned it on land, they were better at remembering it when they were on land versus when they had to remember it underwater. So even though the cue is irrelevant, being underwater had nothing to do with the word list. It's the exact same word list. Just being in the same situation allowed people to remember better. Same thing, later study, even something distracting like a noise. But if you're learning information with noise, and then it's better, people remember better when they're later tested with noise than quiet, and vice versa. And even one's emotional state. So if people are given emotionally arousing words, making them happy or sad during their study, if they're sad when they're learning the word list, they're better at remembering it when they're sad versus when they're happy, and vice versa. So the bottom line is just about anything that can have that can match between when people are encoding the information and then when they have to retrieve the information the better the match, the better memory performance is generally going to be. So, bottom line, any similarity between learning and retrieval helps. At least there is a long list of these kinds of studies that show these kinds of matching between encoding and retrieval can facilitate performance. 12 is the last lecture on to be covered for this exam, and this should correspond to mostly to chapter 7 in the textbook. So we talked about the fact that there's different kinds of memory. It can be carved up, short-term memory and long-term memory, which we already discussed. And in addition, long-term memory can also be explicit and implicit. So we mentioned a lot of studies are done with wordless, which is explicit. But implicit can also take place, unconscious kinds of memory, things like priming, procedural memory. So that's the ability to know how to do something physically. Priming is this short-lived response where some stimulus you just saw a moment ago can direct your behavior there soon thereafter. And explicit memory can be further divided into episodic memory and semantic memory, and we're going to go through these. So explicit and declarative memory are facts about the world that people can actually report. And there's two kinds. There's episodic memory, which involves this mental time travel. You can relive things in the order in which they took place. And that's a very important characteristic of episodic memory, where semantic memory has none of that autobiographical kinds of experience. It's simply a fact that you know. You may not even remember where you learned it. So there's evidence that these are actually, in fact, different kinds of memory from the kinds of dissociations we've talked about in relation to other kinds of cognitive functions. So we have patients who, like Casey, who have damaged hippocampus, and in this case, their semantic memory is intact, but his or her episodic memory is not present. So this patient can't describe reliving an experience, but does know facts from his or her past. And then the Italian woman is the opposite, and so this is a double dissociation. Is able to relive memories for her past, but is missing large chunks of semantic memory. In addition, in terms of brain scans, there is fMRI evidence that these are carried by different parts of the brain. So if subjects are listening to recordings and thinking about autobiographical events or semantic facts. So in this case, they're doing two different types of tasks. Either they're just thinking about semantic facts, things like these are just facts about the world, or listening to themselves recorded talking about autobiographical events. So this is where they're just thinking about or listening to them events that have taken place in their life, and then they're recorded from the brain and measured where there's differential activity. And as you can see in the yellow, we have autobiographical kinds of memory. So this is episodic memory where they're reliving. Oh, I'm sorry, the blue is where they're reliving the events from their past, as opposed to just hearing facts about the world, semantic memory. And one thing to note is the blue and the autobiographical memory, it seems to be concentrated in what we think of as sensory areas. So it's reactivating those sensory areas as somebody's reliving those experiences. Both episodic and semantic memories are usually encoded initially when somebody has an experience. So if you're having a conversation with somebody and they're giving you some information, sometime after that, you're very likely to have an episodic memory. You may remember and be able to relive and have that mental time travel about the experience that you had. But over time, typically the episodic memory will be lost. It's a more fragile, more fleeting kind of memory. And only the semantic information may be left. So you may remember the facts, the information from a conversation or an event that took place, but you may not be able to go back and remember the exact situation, the context, the source, what kind of person you were talking to. You may just remember the facts themselves, and all that's left is semantic memory. In addition to these forms of what we call explicit or declarative memory, we have non-declarative implicit memory, and we already mentioned there's a couple of different categories of this. Procedural memories, things like riding a bike, and associative learning, and we discussed these three different types of associative learning, implicit memory based on associative learning. This is where you have some association between something, some experience, and some sort of object or category. And this can play out and carry over to one's behavior even if one doesn't remember having those experiences. And so we're going to talk about some particular examples. Priming is an example of an implicit memory. And what happens in priming is somebody can be exposed to a list of words or a word or whatever the case may be, and soon thereafter, if one is then tested in a certain way, you can show that sometimes there's an effect of having been exposed to those words, even if one doesn't remember having seen those words. So, for instance, in a famous study by Tulving, subjects learned word lists and had to do a fill-in-the-blanks task, and they were better at filling in the blanks even when they couldn't recall the word. So if they were given a recall test, they may not remember that they saw the word pardon, but then if given a fill-in-the-blanks test, they may be better at filling in those blanks, and they may do it more quickly than somebody who hadn't seen that word list, even though they weren't able to recall it. So it's implicit because they have no explicit memory. They don't recall having seen it, but it's affecting in this case, their ability to do this task. Generally, there's a short-term effect. Priming lasts somewhere in the range of minutes. It does not last for hours or days. And in order to see that this is a distinct type of memory from explicit memory, that implicit seems to be quite distinct, we can look again in the neuropsychological data, and amnesia patients who may have severe interrograde amnesia, and so for instance in a free recall task where they're shown a list of words or they're shown pictures, may not have any ability to remember explicitly what information they saw. And so if you ask them to just free recall the list, tell me what you saw, they may have no idea, they may not even remember that they saw the list. But in a word completion task, like the one we just talked about, they may have just as much benefit as somebody without amnesia from the fact that they saw the list before. So the fact that they saw the word pardon before may actually facilitate their ability to fill in the blanks and say the word pardon now. And that suggests that their implicit memory can remain intact even if their explicit memory is not. And again, this carries over not just amnesia patients. The assumption is that in non-amnesia patients, in regular individuals, these memory systems might be separable because of this kind of dissociation. Another example of this kind of implicit memory in amnesia patients, and this is a object recognition task. So here, what's different about this task and the others, besides being that it's a visual recognition task, is that in this case they were able to show, Warrington and Weisenkranz showed that over days of training, these amnesia patients' abilities improved, and so that they were able to. So they were shown these pictures of the airplane. And over days of training, they were able to recognize the airplane at lower and lower levels of information. So they were able to recognize it, say, originally maybe at D, and then over time they were able to recognize it C and B, and so on and so forth. Even though they would have no explicit memory, if you asked them what they had seen pictures of, they would have no idea. Another example of implicit memory is prejudice. And so that's the fact that people have subjective kind of judgments of things, often based on previous experience, even if one does not remember that previous experience. Some examples of this kind of prejudice in research contexts are things like the fact that repetition can lead to people judging things more favorably, such as advertisements. Even if one does not remember having seen an advertisement before, often that will lead to that advertisement being viewed more favorably. And this is not going to just be for advertisements. So it could be for anything, a product, an object, even a person, perhaps that one has some familiarity with. Even if one doesn't remember having seen that person, it's still going to boost that subjective positivity. Propaganda effect is yet another example of this. So it's just a particularly salient example, a compelling example, because what Begedal showed was that even if people were told that a sentence was false, but then later on were tested on whether they thought that sentence was true or not, the fact that they heard the sentence before made them more likely to say it was true, even if they were explicitly told it was false during encoding. Unless they specifically remember that information that it was told they were false, just having heard the sentence before made them more likely to rate it as true. And so again, this suggests the power of just repeating information, and it tends to make things more believable to people. And we also discussed the IAT, which is one of the COG labs, one of the homework assignments. And what the basic findings of the IAT are is that there are behavioral systematic behavioral slowdown in behavioral responses when somebody has to pair a certain physical response, like a left side button press or a right side button press, with something positive and something that is thought to be potentially they have a bias towards. So, for instance, in the case we discussed, there's a lot of evidence that people engaging in this task with somebody of where they have to judge something as positive and somebody from a different race using the same response, this seems to lead to conflict in the response. It leads to longer response times than when they have to do something that's say negative and that other race. And this suggests, and many people have taken this to mean, that people carry around implicit biases, that these information conflicts. And importantly, this is true even for people who say that they have no such biases. And it's not that we don't believe that they don't have such that they don't. It's not that we think that they're lying that they don't have such biases, but rather the idea is that perhaps such biases are implicit, and that people can be even unaware that they have them, but they can be based on previous exposure to information, and in this case, it's a form of implicit memory. It's based on something perhaps that you don't remember. Maybe you were exposed to certain kinds of associations, and those can carry forth in terms of the behavioral response. And then the question is, does this extend to other kinds of behavioral responses besides button pressings? And as I said, this is something of a controversy. And this was an example of the implicit association task. So you have to respond to, say, a black name or a white name using left hand or right hand. And then you also associate pleasant versus unpleasant to a word with the left hand or right hand. And the critical finding is that, let's say, so white people might have a tendency that if they have to respond to both black and pleasant using the left hand, that may take them longer than have to respond to both white and pleasant using the left hand. And again, this is not about necessarily, it may seem this is about confusion or so on and so forth, but if done properly with appropriate counterbalancing, so half participants will get one order and half the other participants will get the other order, you still see a systematic slowdown when people have to make these kinds of responses, where it's a pairing that is prone to this kind of bias. Procedural memory is skill memory, and the famous fact about skill memory is that it's typically not subject to forgetting. And this is an ability to do this, again, without explicit awareness of how one does it. And it's resistant to forgetting, even in patients like HM, were able to develop new skills, such as mirror drawing. And so procedural memory seems to be, again, dependent on an implicit memory system that isn't as subject to forgetting as explicit memory is. Another form of implicit memory is classical conditioning, and a very particularly strong version of this is phobias, which are thought to often be due to some sort of early experience with something, a negative experience, for instance, with some particular category. And the idea is one can have the fear without having the memory of the original event that took place. And so again, this would be a form of implicit memory because it has behavioral ramifications based on some past experience, but one need not remember the past experience. Finally, we discussed long-term memory and the brain, how long-term memory is encoded in the brain. So one thing we talked about is long-term potentiation. Long-term potentiation are changes in the synapse. So the synapse is that gap between synaptic cleft between an ascending neuron releasing neurotransmitters and receiving neuron. And the idea is that with increased exposure to something, these can change. There are structural changes, perhaps more neurotransmitter release from the sending neuron or more receptors from the receiving neuron. And so this leads to a more active, so now you need just a little bit of stimulation and it gets it going because you already primed, the neurons are sort of already primed to respond in this way. Within the brain, there's certain brain areas that are known to be very involved with memory. Of course, we already talked about a hippocampus, and without hippocampus, we know from HM that no new long-term memories can be formed. The hippocampus is part of this medial temporal lobe structure, and there are a bunch of structures. We didn't really go into any detail in the medial temporal lobe that are involved in memory formation. The last thing we talked about was memory consolidation, and this is the idea that memories begin as being fragile and then are consolidated into a more stable form in long-term memory. So even if something makes it into long-term memory, we're not talking about short-term memory, we're talking about long-term memory, 5 minutes, 10 minutes later. Even if it's 10 minutes later, although it's in the long-term memory range, it still can be a very fragile memory and may not make it and become a more permanent fiber memory. And we talked about two ways that consolidation takes place, synaptic and system consolidation. So synaptic consolidation, this figure should look familiar. Hopefully it's in your long-term memory. And so this is just this long-term potentiation. These changes at the synapse are a form of consolidation, and the point is that this takes place in minutes from an event. These are things that happen very quickly. And so long-term memory is formed in just a few minutes in terms of structural changes at the synapse. A more solid form of consolidation that can last for a lot longer, for perhaps a lifetime, is systems consolidation. And this is where the hippocampus goes and coordinates activity within the cortex, and it sort of offloads the memory from the hippocampus into the cortex and then reprograms the cortex to hold that memory. And once it's in the cortex, it can last for a lot longer. And this type of consolidation doesn't happen in minutes. It happens over days, months, or even years. And the evidence for that comes from cases where this kind of process can be disturbed. So for instance, if somebody sustains a head injury, what you'll see is temporally graded retrograde amnesia. So what happens in this case is that the closer one gets to the point of diagnosis, the less memory that person will have of events that took place beforehand. So if somebody has a car accident, for instance, they often will forget almost all the information immediately before that car accident and quite a bit of the information from earlier in the day. And then as one goes back in time, if it's unfortunately a very serious accident, then the retrograde amnesia could go back decades. And what you'll see is it's graded. So the further away you get from the event, the better the memory may be. And why is that? And the suggestion is that because that memory has been further and further consolidated over a lifetime, our memory continues to get consolidated and it becomes more and more stable and permanent. So this type of head injury can lead to a disruption of this consolidation, and that's why you see this kind of graded retrograde amnesia. Things that are not yet consolidated are now getting disrupted.